Assalamualaikum and hi, I bid to Dr. Maman Hermana, and for today we are from Group 1 want to present to you about the application of Lambda-Rho and Mu-Rho crossplot for fluid identification. So our group consists of me myself, Mama Haikal, and Nabil Aiman, Anik Nakmal, and also Emmeline. So the overview for this presentation goes from the introduction, methodology, result, discussion, and lastly the conclusion. So as you all know, the limit parameters like lambda, which mean the incompressibility, and mu for the rigidity is used to discriminate the lithology. And the gas, oil, and brine were discriminated by using the various rock physics crossplot. And both Mu-Rho and density are better in lithology discriminator, but the density has an advantage over Mu-Rho when dealing with fluid prediction in reservoir. Thus, the cross-plotted lambda-rho and Mu-Rho is effective to be both lithology and fluid discriminator. So I pass the floor to Mr. Anik Nakmal for the objective.
Hello, I am Muhammad Akmal and I'm going to continue this presentation. For the objective, we have three main objectives. The first one is to calculate the parameter needed, which is AI, Poisson ratio, fluid replacement model, Lambda-Rho for either each fluid. And the second one is to execute the Lambda-Mu-Rho crossplot. And lastly, we will differentiate the type of fluid based on the Lambda-Rho crossplot. Now, we shall continue with the methodology for this presentation. So, the first step is we need to do the fluid replacement modeling (FRM) to create the S-wave model. So, the first step that we have here is first we need to go to the processing and we need to double click the FRM as shown in the figure below. Then a process parameter will appear. So for this process parameter, there will be several parameters that we need to complete. The first one that we have here is reservoir. So for this reservoir, we will name it parameter as top gas and base gas. Okay, so now we will continue with the velocity tab. So for the P wave velocity, it will be coming from the P wave log in the well. While for the S wave, we need to compute it. So for the option there, for inside reservoir, we will use the Knunsberg-Castagnard equation, while for the outside reservoir, we will use the Castagnard equation. And below there, we have the figure for density tab. So for this density tab, we will choose the calculate porosity from density in the density porosity option. So by default, we will get the porosity. Now we continue for the in situ fluid tab. So for this in situ fluid, we will choose the 50% water and 50% gas as shown in the top figure there. And we continue for the output tab, which is shown in the figure below. So for this, we need to name all the parameters such as the P wave. We will name it for the P wave 50% brine and 50% gas as shown in the figure. So there is also the QC play button there. So for this button, we can see the model that we create if there is any problem, and if not, if we certified, we can click OK to create all the log. So lastly, the log that we have generated before will be displayed. As you can see from the figure, we have the P wave log, S wave log, density log, and Poisson ratio log. So all this step will be repeated for different FRM output saturation, which is for the 100% brine, 100% gas, and 100% oil.
The second methodology is the calculation of the Poisson ratio for each fluid. The first step is you must open your project manager and then proceed to the log processing and choose other. And then for the second step is by click on the AVO supplement curve, and then the window of the AVO supplement curve will be open. On that window, you must click on the P wave and S wave velocity ratio with the Poisson ratio option. Next, to complete the parameters according to the type of the fluid you choose. And then the fifth step is you must go to the advanced option to change output name on curve according to the type of fluid you choose, either the gas, brine or oil. And finally, after you finish all the parameter, click OK. And the last step is by repeating the process to generate the Poisson ratio log for other fluid, which is for the 100% gas and 100% brine. And the picture shows the step for number 3 and number 4, and the picture below shows the step for number 5. The next methodology is to calculate the P impedance and S impedance for the fluid. The first step is by open the process and choose the log transform and P impedance. And then the second step is to complete all the process parameter of P impedance and changing the curve name and curve output. And the last step is by repeating the process for P impedance and S impedance for 100% oil, 100% gas and 100% brine. And the picture shows the example of the P impedance parameter for 100% oil. And as you can see, the selected parameter is P wave and density of 100% oil, and the curve type and curve name is P impedance. And this is the formula on how to calculate the P impedance and S impedance by using this HRS. So after calculating the FMR, P impedance and also the Poisson ratio calculation, next we continue with the Lambda-Mu-Rho calculation before we can execute our cross plot for the Lambda-Mu-Rho. The first step on the Lambda-Mu-Rho calculation is by going to the process and then choose the log transform, and on the log transform you choose the others, and then finally you choose the LMR window. The second step is by calculating all the parameters of LMR window, and then for the third step is by going to the advanced option to change the output name to Mu-Rho and Lambda-Rho. And finally, you click OK on the LMR window, and the calculation of Lambda-Mu-Rho will be done. And after you finish all the process, you must repeat the process for the other fluid, which is for 100% brine, 100% oil, or 100% gas. And as you can see in the picture, shows the example for LMR calculation for 100% oil, and the picture below shows how to change the output name to lambda and mu-rho based on the fluid type.
So after getting all the parameters set up, we will further proceed by creating the Mu-Rho versus Lambda-Rho crossplot. So in Hamster Russell software, first of all, we go to the Data Explorer and click on the colony well. Then we go to the database option to duplicate the well into tree, and then rename the well based on the percentage of brine, gas, and oil. And for this case, we're using 100% brine, 100% gas, and 100% oil. So then when completed, click Save. Next, in the project manager, go to the process tab and search for crossplot, and after that double click on the crossplot logs, and the process parameter tab will come out, and next select the multiple well, and next we select the type that we want to use, which in this case is the Lambda-Rho and the Mu-Rho for the log type. And next, we insert all the well we have created previously. And next, we set the x-axis as Mu-Rho, while for the y-axis as Lambda-Rho. And then don't forget to change the crossplot name to Mu-Rho versus Lambda-Rho. And then click on the Show Advanced option to change the properties, where we have here is the Mu-Rho for 100% brine and the Lambda-Rho for 100% brine, and then Mu-Rho for 100% gas and Lambda-Rho for 100% gas, and then further Mu-Rho 100% oil and also Lambda-Rho 100% oil. So after that, the graph will show the cross plot, and right click on the graph and choose plot option to start customizing the graph. So in the plot option, we can change the fill color for different fluid, such as In this case, we use blue for the brine, and red for the gas, and green for the oil. So to create the ellipses on the target area, click on the polygon icon below to start highlighting your target area. And finally, click the option and then click on the cross section to generate the cross section of a target area. So in the next slide, we will see the cross section of this targeted area. So as you can see, this is the cross section which showing the targeted area that we have done in the cross plot. So for the result and discussion, we will further continue with Mr. Amalai.
Hello, this is Amlai. I'll be talking about the results and discussion. Well, here are the logins response, in which was created using Gasman fluid substitution, and we delineated our target zone, in which it's between 600 to 650 meters. Now, let's talk about cross-plot analysis. First, acoustic impedance versus Lambda-Rho. In this example, the cross-plots of acoustic impedance against Lambda-Rho distinguish the sand into 4 zones, in which green represents gas, red oil, blue brine, and shale purple. And the lowest values of Lambda-Rho and acoustic impedance associated with hydrocarbon are validated by low bulk density, as shown in the plot. The plot also indicates that both acoustic impedance and Lambda-Rho show good discrimination in terms of fluid content. This is because higher and low acoustic impedance suggests shale and sand respectively, while the different fluid types in the sand lithology are clearly identified from brine to gas by decreasing value of acoustic impedance. So here in this first example, VPVS against Lambda-Rho. So it showed the variation of VPVS against Lambda-Rho for sands and sand-shale sequences. So the plots are better aligned towards the Lambda-Rho axis, thus validating Lambda-Rho a better fluid discrimination tool. So when it comes to the third plot, Lambda-Rho against Mu-Rho, in which also shows the discrimination of sands into 4 zones, it indicates that the Lambda-Rho is more robust than the Mu-Rho in the discrimination of fluids, because the Mu-Rho values are relatively low for reservoir sands. And the right picture, in which is a screenshot from YouTube, it shows the gas zones. So for the first one, the intensity is low in the Lambda-Rho profile. In the second picture, shows a higher intensity in the Mu-Rho profile, which is a characteristic of gas zone. The Lambda-Rho and Mu-Rho plot is effective as lithology and fluid discriminator. But here we are going to use these parameters mainly to identify fluids. So this is the plot of Lambda-Rho and Mu-Rho from the lab data, in which green represents gas, blue brine, and red oil. In general, gas zone is characterized by low Lambda-Rho and high Mu-Rho. So the gas zone has low Lambda-Rho because the presence of the gas in formation causes a significant decrease in its incompressibility. That is, the gas compressed easily when compared to oil and brine. And the oil zone and brine zone has almost the same response. Both are characterized by high Lambda-Rho and high Mu-Rho. And we can see from this picture extracted from one paper, uh, the picture overlying our plot, in which the both gas, in this case gas sands and gas silts, showing low Lambda-Rho and high Mu-Rho, while the brine sands has both high Lambda-Rho and high Mu-Rho. So this is an example of Lambda-Rho versus Mu-Rho, extracted from one paper studying J fields in Niger Delta in Nigeria. So the sands are divided according to the fluid content. So the sands E, F, and G, which contains gas, show low incompressibility, in which is low Lambda-Rho, and high rigidity, which is high Mu-Rho. And the sand D, in which contains brine, show high incompressibility and low rigidity. And that's all for me. I will pass to Mr. Nabil to conclude the presentation. Thank you.
There are three conclusions that can be made from this presentation. The first one is lambda Mu-Rho can be a good fluid separation and indicator when dealing with different properties of fluid. The second conclusion that can be made is lambda Mu-Rho cross plot enable to distinguish different fluid based on its rigidity and incompressibility and can help to detect the presence of hydrocarbon. This is because each fluid, which is the gas, oil and brine, consists of different rigidity and incompressibility. And the last conclusion that can be made is the presence of hydrocarbon can be determined when the value of lambda-rho is high while mu-rho is low. So this is the conclusion from this presentation. So this is the end of our presentation today on the topic application of lambda mu-rho cross plot for fluid separation indicator. And with that, we would like to end our presentation today with thank you and have a good day.